Hello, my name is Glen and I'm a PhD student at the Institute of Theoretical Astrophysics here in Heidelberg. However, today I'm going to be talking about my work that I carried out at Cardiff University looking at the collisions of giant molecular clouds. So giant molecular clouds are clouds of molecular hydrogen that exist within galaxies. They're on the size of around tens of parsecs and exist at a temperature of 10 to 30 Kelvin. The collision of these clouds are quite important to look at because they are one of the theorized ideas of how massive stars form. And massive star formation is quite a highly debated topic within the star formation community. However, the work that I carried out looked at the star formation on a general level regardless of the size. So what did we do? So we made use of a hydrodynamics code called a repo, and we set up two giant molecular clouds spherical of a radius of 20 parsecs. They exist at a temperature of 15 Kelvin and a number density of 100 particles per centimeter cubed. Now these clouds are embedded in a cold neutral medium of neutral hydrogen at a temperature of 150 Kelvin and 10 particles per centimeter cubed. Now these clouds are allowed to collide. We varied the collisional speed, the inclination of the magnetic field, and then the resolution of the simulation itself. So what are the results? So when we look at the collisional velocity, the faster that these clouds collide at, the sooner that star formation is triggered. This is due to the shock forming a denser region quicker and thus forming stars quicker. When we look at the magnetic field, we find that this star formation occurs quicker if the magnetic field is parallel or perpendicular to the collisional axes. So if it's parallel, the magnetic field doesn't really do much to halt the collision, whilst if it's perpendicular, the dense region formed by the shock is allowed to align with the magnetic field perfectly, thus creating the dense structure that we need. When we go into higher resolution, we find that the star formation is delayed, and this is a result due to the turbulence being more resolved. And when you have more resolved turbulence, it means things are not stable enough to collapse into stars. However, the key thing is that regardless of the initial conditions, when we look at when the first star particles form within the simulation, the star formation rate over time, that trend is similar across all 9 simulations, lying within a factor of 2 of each other, which is different from what is claimed in the literature. However, our methods that we use in the simulation is different to what others use in their simulations, so there is good scope for differences within these simulations. So what would be the next steps? Well, synthetic observations of these regions would probably prove crucial because it allow us to see what we should be seeing, and then we can give that information to observational astronomers, and they then can report back and we can adjust the simulations. And also for, in the case of this project, a full kinematic project looking into the kinematics of the system will prove crucial and to see how the turbulence affects the overall system of the star formation going on. So yeah, that's a brief kind of overview of what this poster is about, and I hope you enjoy the poster. Thank you very much.